Today, we want to discuss the adaptive backstepping approach. In other words, for example, in this dynamics, you have unknown coefficients A, B, and C is unknown constants, and x1, x2 are measurable states. And the objective is to do tracking control for x1 converge to track x1d, which is a desired trajectory. Using the procedure, here's the system 1 that we just define a tracking signal. Because it's tracking problem, we define a tracking signal E, which is the difference between x1 and x1d. And x1d is a desired trajectory which you can design. So you substitute the x1 dot dynamics, which is this, from here to here. All this is x1 dot and minus x1d. And x2d is the virtual control input. So we consider this part as y transpose theta because it's a combination of unknown constants. It's a composition of unknown constants. And those coefficients, for example, x cosine squared can be considered as a coefficient of A. So it's linearly parameterized. A cosine, this part is linearly parameterized. Right? You can segregate the unknown constant and the known functions. So you can replace this part by y transpose theta. The y transpose is cosine is this part, okay, which is called a regression matrix. Y is called regression matrix. Theta is the unknown constants. And here theta is A and B plus C. We don't care about B plus C, okay? You can consider B plus C is another constant. Okay, that's fine, because we don't care about what B is, what C is, right? We only care about if the tracking control, which is E goes to 0. And again, adaptive control doesn't guarantee or the estimate theta hat will converge to theta. That's not guaranteed. You only guarantee that E converge to 0 using Barber's lemma. If you check out your solution, your simulation, theta might not always goes to theta. Theta might not always converge to theta, but E does. So you put B plus C here is fine. We don't care much about the parameters. And we define eta as the difference between x2 and the virtual control input x2d. So then we design the virtual control x2d, which is this. So this is feedback term. This is the nonlinear term to cancel out another nonlinear term here. And this adaptive term is to deal with the uncertainties, the unknown parameter terms. And x1d is a feed-forward term to deal with this x1d. Then we can obtain the closed-loop error system by substituting the virtual control input into the open-loop dynamics. So let me write down the closed-loop error system 1. So second system, we reuse this eta. We use eta, and eta dot is equal to x2 dot minus x2d dot. And x2 dot is given by the problem, which is this part, where you can see the control input u. This is the open loop dynamics. So you can see the control input u, then you design the very physical control input u. And this is x2d dot, which is the virtual control from previous system, right? You take the time derivative on x2d dot, x2d, and obtain the x2d dot, which is this part, virtual control. It's now become a little bit complicated because there is another a squared in the second system. It's from x2 dot. It's from the second system. And that a squared is an unknown constant, and that was not covered in the previous y transpose theta hat. That's why we have y2 transpose theta 2. So the y2 and theta 2 become more complicated, but that's fine. So how you got this y2 theta 2 is eta dot equal to a squared cosine x1 minus so you need to take time derivative on each terms, okay? x1 squared so you say this is first term, second term. So first, second is given by the system dynamics here. Expand all these terms, and you can regroup in terms where the way you regroup in terms is you put all the unknown in theta 2. Right, you put all the unknown constant in theta 2 and the corresponding regression matrix, and you will see omega 2 as this, which also show up in here. The only unknown term is theta 2, which is unknown constants, and this is known, which is a regression matrix. This is known, which is this. Now you can design control input. U is designed as this, which is a bit complicated because you have y2 transpose theta 2 hat and y transpose theta hat dot and some nonlinear term, cross terms, feedback terms. So that yields the closed error system 2 and do the double function analysis. And you design the update law for both theta and theta 2. And these are the corresponding adaptive loads, and you will get the negative semi-definite. Use Barbara's lemma to show stability. But the procedure is pretty much the same, right? Except you need to regroup in terms that are resulting from the adaptive terms in the second system. First, according to the dynamics, you have unknown constants in both systems. Eventually, that gives you required two different adaptive laws. That's the complicated part. So you need to regroup in terms twice. That give you y2 and theta 2 here. And you need to take the time derivative here. You need to be careful that when you take the time derivative on some of the parts, and here is x1 squared, because x1 squared, x1 is the first system, and x1 dot contains the unknown constant a. x1 dot contains the unknown constants. So when you take the time derivative on this part, right, that gives you 2x1 and x1 dots, and these parts contain the unknown constants. That's where you need to regroup in terms to different y2 and theta 2. And this term is fine. It's just the predefined desired trajectories. This is feedback terms. This part is also a bit trickier because, but that's fine. That depends on, so you need to design this, right? Usually we design this as gamma yr, okay? Some constant times the regression matrix and the Churchian error, right? And that will also need to be compensated in the control input. That's different from the previous design. And because y regression matrix, which is a function of time, so when you take the time derivative, it's a bit complicated. Y is here, right? And when you take the time derivative of y, because it's function of time, cosine squared t becomes 2 cosine times minus sine. All these are function of time, as well as x1. The control design is structuralized. You follow this procedure and do the regrouping terms and design controllers which include cross term, nonlinear term, feedback terms, feed-forward terms, all these 4 kind of terms in the control design, right? So the only difference part is the nonlinear terms, which is this part, right? This is feed forward, this is feedback. The only complicated part is this, especially when after you take the time derivative. Okay.